Something you should know about Boyle's law, and in fact all the other gas laws we're going to learn about this week, is that they apply to any type of gas. It could be air, which actually is a mixture of gases. It could be helium. It could be propane. It doesn't matter the gas. All that matters is that you're keeping the temperature constant and your sample size constant, and then Boyle's law is going to apply. Again, just a reminder, Boyle's law tells us that if the pressure of a gas goes up, the volume is going to drop. And if the pressure drops, the volume is going to go up. I'm not sure if you guys know this, or I've actually forgotten if I mentioned it in the other video, but if you fill up a balloon with helium and maybe you give it still a little bit of flex, a little bit of wiggle room so that it could expand, if you let it go and it starts floating up into the atmosphere where there's less pressure pushing on the outside of the balloon itself grows larger, just like we saw in that vacuum chamber video not too long ago. And I want to actually even be more precise here about this relationship. It's an inverse relationship, but it's actually an inversely proportional relationship. Inversely proportional. Okay, so the inverse part means if one thing goes up, the other thing goes down. But proportional is actually a bit more specific, and what that means is if, say, the pressure doubles, the volume gets cut in half. If pressure triples, the volume gets cut down to 1/3, and so on and so forth. Or the other way, if we cut the pressure in half, the volume doubles. If we multiply the pressure by 10, or excuse me, if we cut the pressure by a factor of 10, 1/10 the pressure, then the volume is going to have 10 times the pressure. So that's the proportional part. And if you think about the original statement of Boyle's law, that P times V is a constant, that has to be true. Because if you have this setup, and you could call this constant K, for instance, that could be the constant. If you have 2 times your original pressure, call that P1, 2 times your original pressure, then you would have to have 1/2 your original volume, and then you would still end up with K, that constant. Whatever that number happens to be, if you have twice the pressure, 2P1, in order to get that constant, you'd need half the original volume, right? Because, in a way, you can think about factoring that 2 and that 1/2 out. And then all you're left with is just P1 times V1, which we already know is that constant. Okay? So that's what is meant by an inversely proportional relationship. Let's do a few more of these problems here. Number 2 and number 3. A gas holds 2,785 liters of propane. So that's the first volume, 2,785 liters. In Boyle's law, the unit for volume doesn't matter. And here's our original pressure. It's in millimeters of mercury. 830 millimeters of mercury. What is the volume? So we're going to solve for the volume at standard pressure. Now, I told you guys this in the lesson plan document yesterday, but standard pressure is 1 atmosphere. 1 atmosphere is also the same thing as 760 millimeters of mercury. Okay, so we're going to use the same unit. Doesn't matter which unit, as long as it's the same unit. So now let's go ahead and plug into Boyle's law. P1 V1 equals P2 V2. All right, and I'm going to go ahead and rearrange for the thing we're solving for, V2, right there. We can solve for V2 by dividing both sides by P2. Okay, So V2 equals P1 V1 over P2. Now let's plug in what we have. The original pressure is 830 millimeters of mercury. The original volume was 2,785 liters. And the second pressure, the final pressure, is 760 millimeters of mercury, 1 atmosphere of pressure. Now, before we type this in, let's think about what would be a reasonable answer. We're starting off at 830 millimeters of mercury and we're going down to 760 millimeters of mercury. That's less pressure. So we should get more volume. Okay, so let's go ahead and type in the value. Less pressure, more volume. So 830 millimeters of mercury times 2,785 liters divided by 760 millimeters of mercury. And we get, I'm going to have to change the settings on here because I keep doing that same thing. See if I can do Control Enter. And that looks a little bit better. 3,041. In terms of our significant figures, 3 significant figures. The smallest number of significant figures in any of our numbers, 830, has 3 significant figures. So we'll round this and say 3,040. And the unit is liters. That's a reasonable answer. Less pressure, bigger volume. Also, if you look mathematically at what's happening here, this ratio of pressures is really determining what's happening to our volume. Our original volume is being multiplied by this ratio of pressures, and that ratio is 830 over 760. Okay, so the pressure is, in a sense, dropping down by a factor of 1.09, and the volume increases by a factor of 1.09, or it's the final volume is that much larger. One more problem here for Boyle's law. A balloon contains 7.2 liters of helium, the pressure is reduced to 2 atmospheres, and the balloon expands to a volume of 25.1 liters. What was the initial pressure? Okay, so we can solve for the initial situation as well. As long as we read through the problem carefully, we can figure out what we're solving for. So the initial volume is 7.2 liters. It's helium. Doesn't matter. Boyle's law works for any gas. We're going to solve for the initial pressure. The final volume and pressure is 25.1 liters, and the final pressure is 2 atmospheres. Okay, so what would be reasonable? Our volume is getting significantly larger, somewhere between 3 and 4 times the volume. Okay, and so what that means is the original pressure must have been much greater. Less pressure leads to more volume. So we should expect a higher pressure here, kind of compressing that 25 down to 7. Rearranging Boyle's law, you can verify that I've done this correctly, but P1 is going to be P2 V2 over V1. Plugging in our values, 2 atmospheres times 25.1 liters over 7.2 liters. And again, our units for volume cancel out here. Atmospheres will be the unit for our final answer. So what is it that's controlling that change in pressure here? It's that change in volume, right? So the volume is expanding from 7.2 to 25.1. It's that ratio of these volumes here that's going to get multiplied by the second pressure to give us the original pressure. All right, so 2 atmospheres times 25.1 liters divided by, mistype something, 2 times 25.1 divided by 7.2. That's 6.9 6.97. We rounded to 6.9, two significant figures. Okay, so let me know if you have any other questions, and continue on with 4 and 5 if you haven't done them yet.